welcome everybody. We are full again, very good to see. Today it is my pleasure to welcome Enrico Ramirez-Ruiz. Enrico is visiting CFA for quite an extended period, and he's going to be still here for a period longer. Enrico, when he's not in CFA, then he's a professor at the University of California, Santa Cruz. He received his PhD at the Institute of Astronomy at the University of Cambridge in England. And he was a postdoc at the Institute for Advanced Study in Princeton before he started his tenure-track professorship at Santa Cruz. His research interest is mostly focuses on the violent universe with an emphasis on stellar explosions, gamma ray bursts, and accretion phenomena near compact objects. And today, Enrico is going to tell us about recent advances in the understanding of short gamma ray burst progenitors. Please.
Thank you. Thank you so much for having me here, and I've been enjoying my time here tremendously. So I'm going to talk about something that is close to my heart, which is short gamma ray bursts, but I think it's also very appropriate to talk about it in this forum because, of course, Ramesh Narayan was one of the first one to propose that neutron star mergers could be progenitors of short gamma ray bursts, and a lot of the observational work really showing that there's an intimate connection between short gamma ray burst progenitors and neutron star mergers has been actually developed here by Ido Berger and Wen Fei thesis primarily. So I want to first, of course, acknowledge that there's a wide range of people that I have, they're shaped my way of thinking in this topic, and in particularly tons of students, and I see a large fraction of them in the audience. So. And in particular, a lot of the work that I'm going to show is in collaboration with Stefan Roswat, William Lee, who have been my long-term collaborators in this. So this is the outline of my talk. I want to give you some basic ingredients, sort of the necessary requirements that you need to actually explain, the broad range properties of, in general, gamma ray burst and also short gamma ray burst, and we'll talk a little bit about the difference. I'll talk about observations of the host, which I actually think they're being really crucial in pinpointing that neutron star mergers could be the progenitors of these systems, and hopefully I'll convince you, why the arguments I think are relatively solid. And then I'll give you a status report on now the more details about the physical ingredients that are required to produce short gamma ray burst. And we have sort of now transitioned from being an idea to actually looked at the details at every stage in the evolution of the systems and say, can we really have the necessary conditions to explain short gamma ray burst? And I'll talk about future prospects in the field. Okay, so let me start broadly with the basic ingredients. Before I do so, I'd like to show this gamma ray burst just to get everyone on the same page. So gamma ray bursts are sudden intense flashes of gamma rays. As you can see, they're highly variable. And for a few seconds or fractions of a second, they really light up the gamma ray sky. So this is, as you know, Batsy era. And I wanted to just highlight that this gamma ray bursts are in fact the brightest sources in the sky when they're on, and they even overshadow our own sun in gamma rays. Very, very important. We see that these are two spectrum of a low luminosity gamma ray burst and a high luminosity gamma ray burst. We see that they have non-thermal spectrum with a significant fraction of photons above 1 MeV. Yeah? And in fact, if you just simply combine the argument that these systems are highly variable and they have significant fraction of energy above 1 MeV and their spectrum is actually in fact non-thermal, you basically have no other choice but to propose that the source has to be moving relativistically, and in fact, the Lorentz factors that you need to avoid thermalization are of the order of hundreds to thousands. Yeah? And here I put it in the context of, sort of classical high energy objects. And as you can see in nu of nu, they're in the observer frame, they're extremely bright when they're on. So for, almost 20 years or so, we realized that observationally there were these two populations, what we call short gamma ray bursts. This is the duration distribution. They peak around 0.3 seconds. And the long gamma ray bursts, which are about 40 seconds average in duration. And it was proposed that there was certainly more than one progenitor model, but in the last 20 years, we clearly have established, as you know, that long gamma ray bursts are basically directly linked to the collapse of massive stars. And what I'm going to talk to you about is sort of thinking a little bit more about the progenitor systems of these shorter events. And they both show variability in scales of milliseconds. Yeah, so they're highly, highly variable. Something that is extremely important is that their isotropic equivalent luminosities, which are highlighted by these. If you basically assume that these systems are isotropic, their gamma ray total energies are very, very large. Here I put, for comparison, just MC square. This is the population of long gamma ray bursts. They're significantly brighter at peak. Their luminosities are significantly higher. We can see them to higher redshift. And this is now a subset of short gamma ray bursts with redshifts. And as you can see, they're lower luminosity, lower total energy because, of course, they last less. But in principle, this is a fairly stringent requirement. Whatever source central engine you want to postulate, it really has to give you these very, very high energies. So in brief, these are the basics if you want to basically construct a model for gamma ray bursts. You need to provide the energies. Of course, you don't know the beaming fraction. And you don't know the conversion efficiency between kinetic energy and photons. So these could be significantly higher, although we actually know or infer that these systems are beams, so their total energies are slightly smaller than their isotropic equivalent energies. The most difficult requirement is that all this energy has to be in highly relativistic material. And this is actually difficult to do because you have to separate mass and energy in a very effective way such that a large fraction of the energy is at high Lorentz factor, and that's actually, very, very difficult to do. Another important component is, of course, that the seed of this activity is small based on the small scale variability, and that gives you basically a constraint on the size of the systems. And of course, whatever model you put forward, you better explain the rate in which we see the systems, which of course depend very strongly on the beaming fraction. If they're highly beam, of course, the number density of the systems, per year per gigaparsec has to be significantly higher. And this is sort of like the basic requirement. So I'm going to try to sort of combine this and giving you an overall physical intuition of sort of the densities, temperatures, and magnetic fields that you need in these environments to actually explain these systems. And these arguments are very broad. So I'm going to convince you that you need an energy reservoir that has extreme conditions of matter, space and time, and magnetic fields, that the central engine has to be constrained by variability arguments to scales of about 10 kilometers. Unfortunately, the majority, if not all, of the observations that we see come from the reprocessing of the highly relativistic outflow. So the engine, as you know, has to put a significant fraction in this highly relativistic outflow. This is a problem in terms of trying to get observations that tell you something directly about the engine. Why? Because what we actually see in radiation is just dissipation within these relativistic outflows. So basically shocks and particle acceleration taking place in this relativistic outflow provides the clues of, basically how this energy is reprocessing, but it tells you very little about the central engine. Yeah? And something that it's important to always remember is that the central engine is in fact hidden from direct observation. And for a long, long time, of course, that has caused great freedom for theorists, of course, to come with wild speculations, but also it's been, very non-constraining. So in fact, we have to try to infer the presence of the central engine by basically using either observations of their environments or thinking about some sort of dissipation that tells you something about the engine. Like in the case of long gamma ray burst, the dissipation comes from the supernova that we see associated with gamma ray burst. That is directly linked to the nickel production and therefore tell us something about that the progenitor star has to be a massive star, and in fact the star that has lost their hydrogen envelope. So what I want to focus today is to give you a detailed account of basically how in the field we think we can get highly relativistic outflow and what are sort of the constraints that we have in the central engine. And I won't talk too much about the dissipation, but of course there's great advances in understanding the dissipation, and Lorenzo gave a very nice talk last week about some of the salient issues about it. So if you just take the energetics at face value, what this tells you is in fact that gamma ray burst sources, both long and short, have to process about a fraction of a solar mass per second. Yeah? Through a region that it's in fact not much larger than a neutron star or a stellar mass black hole. Why? Well, basically the accretion energy that you get per unit gram, and energetically you know that you basically require these very high accretion rates for a fraction of a second. So what does that tell you if you just take those two things at face value? Well, the first thing that you noticed, this is a very nice plot from Ramesh and Elliott. This is basically the mass accretion rate in terms of the Eddington limit. This is all the sources that we love, particularly in this audience. X-ray binaries, AGN, as you know, they're all basically limited by the photon Eddington rate. So the photon Eddington rate is just basically the balance between radiation pressure and gravity. But as you see, both supernova and gamma ray burst require accretion rates that are at least 12 orders of magnitude above this Eddington limit. Yeah. Is that a problem? Well, no. The energy, in fact, cannot be carried by photons, but it has to be carried by a weakly interactive particle. And if you, in fact, the energy in these systems is actually carried by neutrinos. And in fact, if you use, say, the cross-section for neutrino pair production, and you actually estimate the Eddington luminosity not of photons, but of neutrinos, you get an expression that looks something like this, because of course the cross-section depends on the energy of the neutrinos. But as you can see, these systems are basically sub-Eddington in terms of their neutrino luminosity. So neutrinos are providing the cooling, but they're not providing significant radiation pressure. Okay? So we know that these systems are Eddington limited. You can just immediately, based on the luminosity at Eddington, you can come up with an m dot, and as you can see, the m dot at the Eddington limit for neutrinos is about a fraction of a solar mass per second. You can then easily derive a characteristic density of the environments that you're looking at, and as you can see, the densities are close to nuclear densities. Yeah, so here the majority, if not all, the nuclei are actually photodissociated into both neutrons and protons. This is sort of the environments that you have. And you can also define an Eddington temperature. So the temperature of these systems are tens of MeV. Yeah? And everything is self-consistently from the fact that we're starting by assuming that these are basically Eddington limited systems. So that gives you the physical conditions just solely based on energetics and time scales. And of course, the textbook classical example is supernova, in which the energy is basically carried by neutrinos. And in fact, one of the biggest problems of supernova, at least core collapse supernova, in order to explode, is that they're significantly sub-Eddington, and only a very small fraction of the neutrinos get coupled with the material. Yeah? If they were significantly closer to the Eddington limit, there won't be a problem actually exploding supernovae. So let's think about the time scale. So a nice time scale that you can think of, you can say, well, if I take an object of about a solar mass that it's accreting at the Eddington limit, I can calculate, basically how long it takes the object to radiate its entire rest mass. And that's about of the order of seconds. Yeah? Now that seems like a short amount of time, but in fact, if you compare it with the dynamical timescales in the systems, which are milliseconds, what that tells you is that basically these systems have to be active for thousands of dynamical timescales. Yeah? So compared to the characteristic dynamical timescale of the systems, this mass accretion rate has to be basically there for hundreds, if not thousands, of dynamical timescales. And in that way, they're not that different from AGN or X-ray binaries, no? Because in those cases, we also need to supply mass over a very large fraction of dynamical timescales. Significantly more in this case, but in terms of the dynamics are very, very similar. Another important thing is that you can basically, by equipartition arguments, define the average Eddington magnetic field that you get, and these are of the order of about 3 times 10 to the 16. This is basically magnetar-like field. Not surprising, the magnetic field in these systems basically reaches very close to equipartition, and that in itself gives you another characteristic timescale on luminosity, which is basically, for example, if you were to have a rotating neutron star or an accretion disk, you can release energy via magnetic torques at luminosities that are comparable to the luminosities that you require. Yeah? And here, of course, the characteristic timescales depends very strongly on the magnetic field and the rotation of the object. So this basically just tells you what are the general requirements, and for the past 30 years or so, we know that these are the requirements. This is an old illustration from Stan Woosley, which says, what are the possible avenues in which I can dump a fraction of a solar mass into either a neutron star or a black hole? Yeah? So you need a very cataclysmic event, and not surprising, we know that he was right, and that long gamma ray bursts are in fact supply a significant fraction of the mass to the engine by the collapse of the central core, of the iron core. And the key that has remained sort of open is, well, how we can make this short gamma ray burst. Something that I want to highlight is all these variety of avenues provide the required rates. However, the estimates of the rates are significantly uncertain. Not surprising, advanced, LIGO and the LIGO instrument have, of course, a wide range of possible merger rates. But what I want to highlight, just to give you a feeling, is compare the rates that you need with those of 1BCs of 1As. Yeah? So if you think about, how common neutron stars are made compared to how they merge, they're orders of 10,000, 100,000 times less. Yeah? So these are very, very rare events. And for a long time, there was a range of possible avenues to actually make them. So let me tell you about one particular observation, which I think it's extremely telling. So Wenfei, in particular in her thesis, has done seminal work trying to really understand the locations of the systems. And in fact, if you go back in history to the history of 1As and core collapse supernovae, when we didn't really know the progenitor system, we started realizing their origins just based on their environments. Yeah, we knew that 1A happened in a wide range of hosts, while core collapse happened in very highly star-forming galaxies. Similarly, these analogies perfectly suited to gamma ray bursts, where long gamma ray bursts happen in highly star-forming galaxies, while short gamma ray bursts happen in a wide range of hosts, late type hosts, early type host. Yeah? What that tells you is that there are characteristic wide range of time delays between formation and merger. Yeah? And this is basically consistent with compact mergers. But something actually, particularly to me, that was extremely telling was that there's a fraction of short gamma ray bursts with very good localizations, particularly those in the radio, that have no evident host. Yeah? And Wenfei called those hostless. And when you actually looked at the distribution of this, they're a significant fraction. In particular, if you take into account that our ability to see these objects depends on the external density, and if you're not associated to a host, probably you're moving through a medium that it's rarefied, and therefore the luminosity is lower. So we have a strong selection effect to basically miss these hostless events. Yeah? So a simple explanation could be, well, are we missing them just because they're high redshift? And the answer is no. No? So here, this is work that Peter Barussi and I have done. This is basically illustrating the median short gamma ray burst host mass halo. This is as a function of redshift or look back time. This is Wenfei and Ito's limits. And as you can see, the majority of hosts could have been easily seen to, very high redshift. And in fact, if you look at the limits here compared to how many you expect for a wide range of time delay distributions, you're still about an order of magnitude. So what that tells you is that you cannot hide all of these host lists at high redshift. And in fact, what this tells you is that whatever progenitor system you require was able to actually escape the host galaxy. Yeah? And that's actually not an easy feat to do. So to me, that was probably one of the strongest constraints. And in fact, if you look, so this is the median mass of a galaxy. If you basically assume that your progenitor system gets a kick velocity of about 90 kilometers per second with some wide range distribution, you can see the number, the hostless fraction that you get are only progenitor halo masses that are small. These have basically weak velocity dispersions, and the fraction of hostless halos are not very high. But once you push the kick velocities to about 360 kilometers per second, as you can see, a very, very large fraction of the system are able to escape basically the gravitational pull of their host. So if you follow this argument, here I show basically what are the sort of average velocities of the systems that you require to get the hostless fraction that it's observed. And remember, this hostless fraction, it's really a conservative estimate, given that we're probably likely missing a lot of them. And as you can see, you really require kick velocities that are in excess of 180 kilometers per second. And that, to me, is basically extremely telling on the nature of the systems. Why? Because if you actually looked at the cumulative velocity distribution, as you know, the systems get a kick when the neutron star is born. That immediately tells you that in order to get those high kicks, a neutron star has to be involved. And in fact, if we plot here the observational constraints, you see that the only two available systems to do it are either neutron star mergers or neutron star black hole mergers. Yeah? So this is very telling in sort of indirectly determining that the systems are basically have to be involved. And everything that involves a white dwarf, as you can see, doesn't really get significant enough kicks. And here, of course, I didn't highlight black hole mergers because they have no available accretion supply. Yeah? So we don't actually think that they can produce short gamma ray burst. Okay, so that, in my view, is one of the strongest arguments. And in fact, I'll give you another in due course. But in my view, the fact that these systems are able to escape the host galaxy, that basically immediately rules out a wide variety of alternatives that we thought. So how far have we advanced in actually understanding these systems? So let me give you a hopefully pedagogical overview. So as you know, these systems, once they're assembled, as we know, the majority of double neutron stars in our own Milky Way are going to merge in less than a Hubble time with a wide range of time delay distributions between 100 megayears to about a gigayear. We understand this phase extremely well. We can actually predict the gravitational wave signals in extreme accuracy, as of course driven by the requirement of actually having templates for advanced LIGO. Things actually become significantly more interesting once the two objects come close enough together that they cannot be treated as point masses. Yeah, and this is basically where the dynamical stability onset takes place. And this is really where a lot of the details of the physics starts to matter. So I'm going to focus about what happens to the merger remnant and what happens to the unbound debris first. But before I do so, let me just give you an overview of what actually sets this dynamical instability. So the way that you can think about this is I have two neutron stars. Here I'm assuming that they're the simplest objects that I can make, which basically are objects made by a polytropic equation of state. What does that mean? Well, that means that when this Lorentz factor is when this adiabatic, is the polytropic gamma index is very high, the equation of state, we call it, is very incompressible. Why? Because you can think about if this is high, a very small change in density is going to produce a very large change in pressure. Yeah? So that means that if I compress it a little bit, the pressure goes up, and it actually prevents me from compressing it. And as a result, if I show you a neutron star made that way with a gamma 3 equation of state, as you can see, it's almost constant density all the way to the edge. Why? Because I cannot pile a significant amount of matter in its interior. As you know, the equation of state is highly unknown, so this basically illustrates our ignorance. If this is basically small, like a 5/3 adiabatic index, it's highly compressible, and as a result, I can put a lot of mass in the inner part, so it's a very centrally condensed star. Yeah? And as a result, if you contrast this two, this object has significant mass in the outer parts, while the very highly compressible equation of state doesn't. Yeah? So what, in fact, sets up the dynamical instability at these systems are getting closer and closer, where in fact is the steepness of the effective interaction potential, the tides. And what I show here, if these objects were point masses, this is the angular momentum distribution. Of course, these, since basically they have no side, it's just a simple line. But as you can see, once they have structure, you get this minima. And this minima comes basically for the steepening of the interaction potential and from the tidal effects. Now, not surprising, if the equation of state is basically highly incompressible, there's a significant amount of mass in the outer parts of the objects, and these objects become dynamically unstable at large distances. While if they're highly concentrated, you have to bring them significantly closer together for them to become dynamically unstable. And this is very, very important because in some ways, we think that really understanding where these sets place tells us something about the equation of state. Interestingly, these very incompressible neutron star becomes dynamically unstable, and the dynamical instability is purely set by Newtonian effects. You actually don't need to do any general relativistic corrections for the instability, and in fact was highlighted by Chandrasekhar a long time ago. Now, as a result, if I looked at the power spectrum of gravitational waves, which is shown here for a black hole neutron star, this is by Shibata's group, he changes the equation of state from hard to soft. What does that mean? Well, it means that soft is highly compressible. So what does that mean? If I have a highly compressible equation of state, I can get the neutron star closer and closer, and therefore I have significant power at high frequencies. While if I have a very incompressible equation of state, the objects become dynamically unstable at larger distances, and there's basically no high energy power, high frequency power in the gravitational wave spectrum. And that's why the gravitational waves carry, very, very vital information about the structure of these systems. Okay? So again, a very large uncertainty in trying to understand the fate of these systems rely on or lack of understanding of the equation of state. So let me give you a detailed example. So this is some of my PhD work. Here we use a relativistic mean field equation of state. You probably not see this, but this is for this relativistic mean field equation of state. What is the effective gamma? As a function of radius, and as you can see, it gets very close to 3. Gets a little bit higher and then decreases. So this is extremely incompressible equation of state, and these are the density profiles of the neutron stars that we made, and as you can see, they're almost constant density because they're so incompressible that you cannot pile up any mass. And this is the electron fraction, which just tells you the ratio between neutrons and protons, and the material is extremely neutron rich. Okay, so I decided to show you this movie, not because it was the first calculation I did, but also because it has several issues with it, which I think in some ways highlight the importance of understanding the physics. Okay, so you set up these objects very close of them becoming dynamically unstable because you don't want to spend all your computational domain for these things to go in the secular phase. The objects become dynamically unstable. You get mass shredded in the outer Lagrangian points. A very small fraction actually of the mass is able to make it above the escape velocity. Check the time here. in only sort of tenths of milliseconds, you get basically these differentially rotating remnant in the core. And really understanding what happens to that merged core, it's very, very crucial for what I'm going to tell you. I don't know if you realize, but there's something that is extremely wrong with the simulation and our initial conditions. The two neutron stars are actually tidally locked. Yeah, they're actually completely coupled with each other. And in fact, that's an extremely unrealistic condition. Why? Because the viscosity that you need in order to have these two neutron stars being tidally locked is extremely high. Yeah, so a much more realistic initial condition is, in fact, having completely rotational. But of course, for computational simplicity, when they're tidally locked, they're easy to simulate. But that's a very important thing, that the viscosity inside the systems is very, very small. Okay? So for the past 10 years, we now basically can do these simulations. Something that I forgot to tell you is that, in fact, at the end of our simulation, the escape velocity of the merged remnant is about 0.3 c. What does that mean? The equation of state that we have is not strong enough to support it, but it's actually supported by differential rotation. Yeah? And in fact, because we're doing a fully GR calculation, we stop at about 10 milliseconds or so. So the field has really exploded in the past 10 years, where we now have a general relativistic framework with neutrino transport and magnetic fields. Yeah? The first thing that I want to highlight is a guarantee electromagnetic signature that we have is basically the unbound debris that is ejected in these outer Lagrangian points. And we need to know the energy and mass content of the unbound debris. This has been done for, I counted 7 different groups. And the consensus is that the mass ejected in the outer Lagrangian points is anywhere between 5 times 10 to the minus 3, 5 times 10 to the minus 2. And the escape velocity, or the velocity of these tails, is about a fraction of the speed of light. And this depends very strongly on where the outer Lagrangian points are, which depends on the equation of state. Okay, so this is a guarantee electromagnetic signature. Why? Because this system is radioactive. It's basically purely our process material, very heavy elements, which are constantly decaying. So very similar to a supernova, where you have material that is basically expanding and energy is being injected to fight adiabatic expansion. These systems are thought to actually produce these infrared transients that you see here, and work that's been done here and by Neil Tanvir's group show that these infrared X's that we're seeing after the standard afterglow in short gamma ray bursts seems to be consistent with these mass ejection in the outer Lagrangian points. Now, of course, it's only one point, it's only one axis, and what we would like to know is basically whether or not there are any spectral signatures that, in fact, this material is powered by the radioactive decay of these very heavy nuclei. And to some people, this axis, infrared axis, is also a very strong signature that, in fact, these short gamma ray bursts are powered by these neutron star mergers. Okay, so this is where the huge debate in the field begins. And it's basically, what is the fate of the merger remnant? Does it collapse to a black hole or not? And of course, that very strongly depends on our ignorance of the equation of state and whether or not we have an equation of state that can support the merger remnant. Why is there so much debate? Well, because the two avenues to actually produce a short gamma ray burst that have been discussed, one is basically the object collapses to a black hole. It leaves an accretion disk in this sort of very pristine environment. Accretion basically provides the magnetic field energy, and the spin of the black hole is your main energy reservoir. And here, the duration of the short gamma ray burst is given by the viscous time of the debris, which is of the order of a second. Okay? I'm biased to that alternative, and I'll argue why I actually think that the second alternative doesn't work as well. So if, in fact, the merger remnant is stable, we know that there's so much differential rotation that, in fact, instabilities like that of the magnetorotational instability can amplify the field to very high values, and you're left with a stable hypermassive magnetar. And the argument is that then the magnetar can basically power the burst. And where is the energy coming from? Well, the energy coming from the rotation of the merger remnant, which is of the order of about 2 times 10 to the 52. One of the problems, of course, is that if you really want the magnetar to spin down in a fraction of a second, the luminosities accompanying that are very, very high, and they're in significant excess with those of short gamma ray burst. And in fact, work that's been done here by Wenfei has actually shown this is the isotropic equivalent energy distribution. And when they're able to measure the size of the jet, they get of beaming fractions that are about 100, and they are calculating kinetic energies of about 10 to the 49 ergs. Yeah, so there are basically strong constraints in the kinetic energy content. You can say, well, I'm only seeing the highly relativistic material. Am I missing any energy from these explosions? The way to do this is actually to follow this in the radio at late times. And as you can see, the limits are extremely deep. And the consensus in the field is basically that the kinetic energy content of this explosion is actually small. And in fact, much smaller than the total amount of energy that it's available just on the spin of the neutron star. Yeah, so that's one constraint. If it's really a magnetar, why is it that we're not seeing the 10 to the 52 ergs being actually injected into the external medium?
You mean the total kinetic energy, not the relativistic part?
Yeah, the total kinetic energy. I mean, here I think you need Lorentz, you still need transrelativistic material to get, bright radio. But yes, so the short GRB measures gammas beyond hundreds. And now we know that even if you go to gammas of a few, there's still, very little kinetic energy being injected into the environment. Okay, so I'm going to give you a little bit of detail as to why there's so much debate as to what happens to these remnants. So here I show the same simulation, and what we're trying to understand is the fate of this merger remnant. So why it's being so highly debatable? Well, the first thing that you notice is that this remnant, this is like a Keplerian velocity distribution. The remnant is differentially rotating. What does that mean? That it's actually supported by centrifugal forces. So if you take that as a given, you all know that when you have a differentially rotating object, you always tend to approach rigid rotation when you act upon processes that transport angular momentum. So the big debate in the field is actually, can we understand what are the mechanisms that transport angular momentum from the system and basically allow it to collapse to a black hole? A big debate is also that these hypermassive neutron star cannot settle into rigid rotation if the mass exceeds that allowed by rigid rotation. So in some ways, the equation of state tells you, can I support an object that is 2.6 solar masses or not? Even if it was, and particularly when it's not differentially rotating, the equation of state has to do the job. And the question is, could we get a stable object, or that object is going to collapse? And that means also that how long it will take to collapse to a black hole tells you what are the main processes that are removing angular momentum from the system. So you get a basically system whose escape velocity is only 0.3 c, but that the equation of state cannot support it. And the question is how long it will collapse to a black hole. And the problem is that it's very complex, because we know that there are Barr-Mauldin instabilities, gravitational waves that drain angular momentum from the system. I'll show you there are significant amount of neutrino-driven winds, and magnetic fields play a very important role in mediating the transport of angular momentum in the system. So for the past 10 years, different groups have actually decided either focusing in really doing very detailed microphysics and understanding the neutrino. Some others have focused in doing the magnetic fields well. So I'll show you a sort of a wide range of arguments that apply to very particular Taylor simulations that basically try to get one of the physical mechanism and understand its purpose in determining this. And I'll tell you that in fact understanding this time delay to collapse of a black hole, or whether or not you even get a collapse of a black hole, is very important. So this is the time scale, one of the time scales that you have to deal with, which is this object, this merger remnant is hot. So you also have basically neutrino pressure. there's significant amount of heat, and this heat basically has to radiate away from the object. So here this is a hypermassive neutron star that cannot be supported by the equation of state, but is supported by basically the thermal pressure content. And as you know, this is very similar like turning off the sun. As we know, if we return the nuclear reactions of the sun, it'll take the Kelvin-Helmholtz timescale for those photons to escape. Here, the neutrinos are doing the job, and it takes of the order of about a couple of seconds for the neutrinos to leak out. And as you can see, after sort of hundreds of milliseconds, the collapse has taken place. Now, one of the problems is that this system is so hot and radiating so many neutrinos that it's actually polluting the environment with huge amount of mass. These are the mass wind laws that you get from neutrino-driven wind, which is about 5 times 10 to the minus 4 solar masses per second. Now, we're used to think of stars per year. 10 to the minus 4 solar mass per year is already very high, but here you're basically 8 orders of magnitude above that. So let me guide you through some of the timescales. So of course, the dynamical timescale here is very, very short, of the order of fractions of milliseconds. If you have gravitational waves being very effective, they act in multiples of this dynamical timescale. One of the very interesting things is if you actually just take the viscous dissipation, which is in fact dominated by neutron transport and thermal conductivity, the timescales are very, very long because, as I was telling you, the viscosity inside the system is tiny. Yeah? So the physical viscosity of the system plays no role, and in fact, everyone believes now that in fact what mediates the collapse is magnetic fields. Yeah? And as you know, magnetic bracking on differential rotation acts in some multiple of the Alfvén wave speed, and here, if you have a 10 to the 12 Gauss pulsar and you don't amplify it, the time scale could be as long as 100 seconds. But what we see is that amplification takes place very, very quickly, and collapse therefore follows. So let me show you this example. This is a GR MHD simulation. This is a differentially supported remnant, but the MRI is very, very effective. It amplified the field to a fraction of equipartition. You see the transport of angular momentum, and then you get a black hole and an accretion disk on 20 dynamical timescales. Yeah? So less than hundreds of milliseconds, the collapse takes place. So why is it that we are so concerned about this timescale of collapse? Well, the reason is because, as I was telling you, there's so much mass being ejected from the system that, in fact, if you want to produce a relativistic outflow, there's so much barium pollution that, in fact, it's very, very difficult to get to very high Lorentz factors. Yeah? Remember, a Lorentz factor of 1,000 means that, the energy per unit mass, it's very, very low content, and if this system is basically ablating so much mass, it's very, very difficult during that time to produce a relativistic outflow. So what we are thriving for is to get a pristine environment as quickly as possible, and that requires the collapse to be very, very fast. So this is an example of how much mass is ablated from the system. This is, the neutrino-driven winds. The mass outflows are about 10 to the minus 4 solar masses per second. And as you can see, even though the poles are slightly less depleted with mass, it's very, very difficult to actually produce a relativistic jet. And what we actually have shown is, in addition, if you produce a relativistic jet, the jet has to make it through all this mass. And in fact, it can't. Yeah? There's so much ram pressure here that if you want the jet to punch through this, it's actually very, very difficult to do. So the argument, I think, that a large fraction of the field has gone through is that, in fact, black hole accretion is basically very important, and that the collapse has to be fast. And once those two key physical ingredients are satisfied, then the mass accretion rate is basically given by the size of the disk divided by the viscous timescale. And this environment is very pristine. There's no mass ablation, and then you can get a relativistic jet. My argument against the magnetar model, particularly if it's stable, is that the Kelvin-Helmholtz timescale of this excess heat is about 2 seconds. So for 2 seconds, you're polluting the environment, and 2 seconds is the maximum duration of a short gamma ray burst. So in fact, it's very, very difficult to, in fact, have a very, very pristine environment to do this. So it seems, and I'll tell you what are sort of the constraints of this requirement, the prop black hole formation. It's needed, and it's a key ingredient. Here, I just show a simulation that, in fact, where the neutrino-driven wind is actually active for 100 milliseconds, and the jet that precedes the collapse is active for 2 seconds, and as you can see, the jet actually can make it through. So a big problem also for these, once you really go into the very details of the systems, is that if the collapse is not very, very fast, then you're enshrouded by this neutrino-driven wind, which has tons of ramp pressure. So in some ways, the duration of the gamma ray burst has to be significantly longer than the duration of this wind. Yeah? And if we see a short GRB that it's 100 milliseconds duration, the collapse better be very prompt. Otherwise, you get into trouble. Okay, so this has very interesting consequences. So what I show here is if you take the current population of double binary neutron star and you do a population study, you can basically predict what is the total mass of the remnant after the two neutron stars merge. And what we show here is the fraction of systems that actually have prompt black hole accretion versus a stable magnetar as a function of the maximum mass that can support a non-rotating neutron star. And what you can see is that if that mass is below 2.4, the majority of the systems collapse promptly to a black hole. But all of a sudden, if this equation of state is such that it can actually support cold neutron stars above 2.4 solar masses, then a large fraction of your objects are in fact stable magnetars. Yeah? So this is extremely interesting from the perspective of advanced LIGO, because we can basically calculate in some ways the rate of short gamma ray burst versus that of advanced LIGO. And that will tell you basically whether or not a stable magnetar is actually left or black hole accretion. So as you can see, this requirement of prompt collapse is intimately linked to the equation of state of nuclear matter, which we don't know very well. So this is something that now many groups are pursuing and trying to really understand whether or not we can see the signatures of that in the gravitational wave. Okay, so just to finalize, let me now, if I brought you into this idea that black hole collapse basically has to take place. I didn't tell you very much from the fact where you have a black hole and a neutron star. Here, of course, you already have a black hole with an accretion disk, but we believe that these avenues basically less frequent. And the key is basically how big are the disk after the collapse takes place, and that also depends very strongly on the transport of angular momentum. If the transport is not very effective, you get basically very little disks, and if the transport is effective, you can get large disks. And in fact, also an important component here is the mass ratio between the two systems. So if you these systems are actually relatively nice to model and much easier to understand. Why? Because everything just depends on the mass of the disk. So let me just give you a quick review of the main properties. So here m dot, which is the mass accretion rate into the black hole, depends on the size of the disk and the viscous timescale. So just for these, the sake of argument, grant me that the viscous timescale is basically equal and that the m dot only depends on the mass of the disk. So if you have a disk that is very massive, the neutrinos are are trapped. What does that mean? I'm getting close to the neutrino Eddington limit. Once the majority of the neutrinos are trapped, here basically I have a system that is basically Eddington limited. In fact, not only Eddington limit, but it can be actually gravitationally unstable because the mass of the disk starts being comparable to the mass of the black hole and gravitational instability set in. We actually think that that never happens and that the disks that we have are more or less around this region in which the neutrinos are slightly opaque, but the disk is actually very effectively cooled by neutrinos. There's also a very interesting transition here, which is that the inner parts of the disk are basically neutrons and protons, and that the outer parts of the disk are actually alpha particles. So if you actually think thermodynamically what you think it will happen if you transition from here to here, as you know, alpha particles are significantly more bound than neutrons. So when you go through this transition, actually you get energy from the system. And in fact, you get what we call a recombination, an alpha recombination wind, in which the disk is actually losing mass just because it's recombining into alpha particles. So there's lots of interesting things that we can simulate. So let me just give you an example of these calculations. So you choose the mass of the disk, and then you let it evolve viscously. And as you can see, you can do these calculations in 3D. This is with Harm 3D Scott Noble. He can do these easily with 10,000 or so dynamical timescales. And here what we're seeing is basically that the time scale of the duration of the short gamma ray burst is just given by the viscous time scale of the accretion disk. We now are in the process of actually trying to do the microphysics right, because this is, for example, if you have an adiabatic equation of state, but if we put neutrino cooling, you already start seeing the effects of neutrino cooling. No calculation has self-consistently put neutrino cooling and alpha recombination to really try to understand the evolution of the systems. But this is very standard now in global models of GRMHD, in which you clearly see that you have a turbulent field that is basically built up by the MRI. You get these equatorial outflows, but more importantly, you get this Poynting flux dominated outflow where we actually think the highly relativistic core is actually made. Yeah? So these black hole systems are very pristine, and in fact are rather reminiscent of things like blazars or X-ray binaries. And for example, a big problem remains today is that why is it that microquasars have Lorentz factors of only a few, blazars of tens, and gamma ray burst of hundreds? Yeah? And that has to be directly linked with the microphysics of the accretion disk. That's the only thing that it's not scalable. And I don't have an answer for you, but that's a very big open question. Okay, so just to summarize, we are now in the stage in which we're now building very, very detailed models and try to understand the processes between the neutron stars becoming dynamically unstable, the ejection of the tidal tails, and the sort of infrared transients that Ito and others have claimed to have detected. And more importantly, a lot of work is basically now underway trying to understand, once these systems merge, what happens to the remnant. Yeah? And whether or not it can be supported, that depends more on the nuclear physics. And of course, I will invoke that in fact you need collapse, and that this collapse will naturally lead to a Poynting flux dominated outflow where you can actually very nicely take the gravitational binding energy and put it only in a very few ions. Yeah, because for a Lorentz factor of about 100, you really have to break basically energy and mass very effectively so that only very few particles can carry a large fraction of the mass. Okay, so my summary is just that the hostless burst basically tell you that whatever model you need has to have excess of 150 kilometers per second to escape their host galaxy. That uniquely points out into the realm of compact binaries. We now know that the inferred time delay distribution, kick velocities, and the transients are all consistent with those expected from compact binaries, but of course we don't have a direct evidence because remember, we're always seeing the reprocessing of the kinetic energy and nothing else. I will argue that the presence of these long-lived magnetar is not supported by theory, at least if you want to power a short gamma ray burst, and it's strongly constrained by observations. And if you really want black holes to form quickly, that puts constraints on the equations of state. So now you can start making statements about how these mergers end their lives. And something that I think people are very excited is if this prompt black hole formation is essential, you can try to basically compare the LIGO rates with the short gamma ray burst rate and basically try to learn something about like every single merger collapse to a black hole or not. And I'll stop here. Thank you.
You introduced about the type of the host galaxies, and in your advice, you give the progenitor for the gamma ray burst without the host galaxy is about the black hole and the neutron star or two neutron star. I wondered how about other gamma ray bursts with host galaxy? It is possible that we use the host galaxy type or the distribution of the gamma ray burst within the host galaxy to give the constraint to the progenitor of those gamma ray bursts.
Yeah, so the general statement is that there's a wide range of peak velocities and there's a wide range of time delays. No? So for example, if you have a short time delay of 100 megayears, the likely population that you're going to be related to is a star, a galaxy that is still forming actively stars. Well, if you have average time delays of gigayears, you start really seeing ellipticals, mainly being your host. So we can do that in a statistical way. You're absolutely right that doesn't rule out the possibility that basically all the short gamma ray bursts in star-forming galaxies could be different progenitors than those in late-type galaxies. Huh? But I think the unifying theme is this idea that the kicks are abundant, and in fact, if Wen Fei was here, she will argue that in fact just looking at the location of where these happen in the galaxies are very extended. If you saw in her montage, you see basically the half-life radius, and these objects are very, very far away, 10 times sometimes even away from the half-life radius of the galaxy, which tells you that they may not have escaped, but they basically have traveled relatively far away from their birthplace, and in fact, the distribution of offsets from the light tells us also something that the systems have to have had a very strong kick. But you're absolutely right that in principle, for example, another alternative is if you make them in globular clusters, as Josh has invoked, you also expect, globular clusters are significantly more extended than the light. If you can find a progenitor that does it, and they could be a multitude of progenitors, as now people believe it may be the case in type 1As. But the simple hypothesis was the one that I put forward, which was just basically something that fits, one model that fits all observations, seems to be this compact binary merger.
Okay, you had a question?
You described to some extent the nature of the central engines in short gamma bursts. But what about the central engines in these objects where you don't see a gamma ray burst, but you are actually see relativistic outflows? What is the nature of those central engines?
I mean, you're referring more in the context of core collapse. Yeah, so I think in the context of core collapse, if you think about the nature, and Rafaela will be here, she will argue that the sort of mildly relativistic supernovae are a factor of 100, if not 1,000 times more common than long GRB. So what I would tend to argue is that in fact, getting a Lorentz factor of 100 is a very unique occurrence. And we don't really understand basically the specific conditions that are required to get a core of Lorentz factors that are that high, but that nature basically fails most of the time, and that most of the time, baryon pollution is very, very effective, and you only get to, Lorentz factors of a few. And in fact, this is sort of what we see. I mean, we see that type 1bCs seem to be relatively well explained in the radial properties just by the shock acceleration of a spherical blast wave. But in fact, once you start going above a fraction of the speed of light, you really need to break it into these objects have to have a core, and that core has to be mildly relativistic. Now, in these systems, we don't know, what are the analogs of low velocity, and people in the advanced logic community feel like, oh, can we see a short gamma ray burst emanating from those? And the answer is, based on the beaming fraction, no. There won't be any short gamma ray burst pointing towards us in the advanced LIGO volume. So you really have to rely on other electromagnetic signatures that are not these highly relativistic yet pointing at you. And we don't really know whether, only a very small fraction of those are able to do, to make short gamma ray bursts. But yeah, I will argue that dividing energy and mass very efficiently happens very rarely in the universe.
Okay, so last question.
How far do we have to go before we can use GRBs as standard candles? Because it's interesting that you found that 2 to 2.4 solar masses is kind of potentially the mass of a lot of the progenitors, which is a bit analogous to the type 1a supernova, where there's some standard mass, which essentially means you get the same luminosity.
Yeah, so if you think about using them and standardizing them based on their light properties, sort of gamma rays, or I think that's probably never going to happen because we don't really have a very clear way of standardizing. What people are very excited is that in fact gravitational waves give you the amplitude and the distance. So in some ways you can use them as a standard candles once you have the gravitational wave detection. And in fact the amplitude will tell you something about the combined masses, as you were saying. It won't tell you, how much mass remains because actually, once you go to very high frequency, the merger is out of the advanced LIGO volume, so we're never really going to see them collapse. But yeah, so people are excited about using them, but once you have gravitational waves, I think with photons it's going to be difficult.
Okay, so Enrico is going to be around.
Thank you.
Thank you very much.